All right, guys, this is lesson 2.5, which is dealing with free fall kinematics problems and how to solve those. So I'm starting with the equation that we would use to solve. And again, it's the same process. We're going to draw a picture. We're going to set up our table with our unknowns. Then we're going to select the right equation, and then we're going to do the algebra and solve. So the first problem here says a construction worker drops a brick off of a building, and we want to know what is the velocity of the brick after it's fallen for 4 seconds, and then how far has the brick fallen during that time. So if this is my brick here, and I'm going to drop it. Drop is an important word because it implies, because again, sometimes you have to use context clues, but it implies that the initial velocity is 0. So we're not throwing it upward with some positive velocity. We're not throwing it downward with some negative velocity. We are just dropping it, so the initial velocity is 0. So it's starting at rest, and then it's going to fall downward, and it's going to speed up on the way down. So it doesn't say that it hits the ground, but we know at 4 seconds is when we're kind of looking to examine what's going on. So that's the first step, drawing the picture. Second step is this table. So change in position, or the displacement in the y direction this time. Vi initial velocity, Vf final velocity. Instead of having acceleration, we have g, the concept of the acceleration due to gravity, which is a constant on Earth, and then delta t. So we can always plug in negative 9.8 meters per second squared for the acceleration due to gravity in all of these problems. So as long as you're on Earth, that is the acceleration due to gravity. We just got done saying that the initial velocity would be 0 because we're dropping it. And we are looking at a time of 4 seconds of falling. So that is what we're dealing with. In part A, we want to know the final velocity after 4 seconds, so we're going to do that. And this box here is the one that is not involved. So delta y is not involved in the equation. So if I go back a slide and I pick the equation without delta y, the equation without delta y is the first one. So I'm using this. That's not what I'm to try that again. I want to grab that equation and bring it to the next page. So send to current page. There we go. And that's what we're going to work with. So for part A, we're going to use this equation. So we've selected the equation, we filled in the chart. So from here on out, it's just doing algebra. So most people are pretty good at this idea. So for VF, that's what we're solving for, so I'm just going to leave it as VF there. We're looking for the initial velocity, which is 0, gravity, which is negative 9.8, and then the time is 4. So we're just going to multiply the 9.8 times 4. There we go. And for part A, you should get a value of something like negative 39.2 meters per second. Again, the negative implies that it's moving downward, so that's good because the brick is falling. So that's part A. Part B wants to know how far it's fallen. So for part B, we are looking for this question here, delta y, and we can use any equation that we want because we now have 4 out of the 5. So if I come back to the equation sheet, I'm going to use the one that looks easiest, which is the last one here. So I'm going to pick that equation and bring that over with me. Again, on the test or quiz, you're going to have the equations there that you can use, so you're not going to have to worry about memorizing these. You just use them. So plug that in. Shrink it a little bit because it's a ridiculous size. And then we're going to go ahead and plug in for what we're looking for. So we're looking for y, and that's equal to, and let me shrink this a little bit. So we have the 1/2 value, initial velocity, which is 0, the final velocity, which is negative 39.2. It's important you put in the negative in these equations because if you don't, you will not get the right answer. And then the time is 4 seconds. So let me draw in the little delta symbol here for a triangle for change in y. And if we keep going, we just put that in the calculator, and you should do this on your own to make sure you're getting the same numbers. But I got negative 78.4 meters. So that also makes sense that it's negative because it is falling downward. So pretty similar to what we did in the kinematics, the horizontal 1D kinematics problems, but now we're just working vertically. Okay, let's try the next one here. So the next one here, we have a tennis ball that we're going to throw upward with some velocity. So there's that picture. Thrown upward with an initial velocity of 22.5 meters per second. It's caught at the same height, so it goes up, slows down on the way up, so the air gets smaller, reaches the apex, and then it's going to come back down. So I'm just trying to there we go. Comes back down, and it returns to the same level. So we've looked at this example here in previous problems. So there's the tennis ball has somehow changed color as it got up, but you get the idea. So so good enough picture. Filling in the table, and we'll figure out what we're looking for. So again, delta y, vi, vf, g, and change in time. So the initial velocity is going upward at 22.5, so it's a positive 22.5. That's meters per second. Gravity is always negative 9.8. And that's all the numbers that are kind of given in this problem. So it says, how high above the release point does the tennis ball go? So we're kind of looking for how far it goes up. And I would call that delta y. So we're looking for delta y in that one. So I'm going to put a question mark there. B says, how long is it in the air? So that's the time up plus the time down. That'll get us our total time. And that's part B, is the time in the air. And then C is what velocity is going with when it returns to the same level. So those are the ideas. Now, if it seems like it doesn't give you enough information, it usually means that one of the values is implied, or you should recognize it from the situation. So the thing that we should recognize is that at the apex, which is how high it goes in the air, we know the velocity at the apex. So in the last lesson we said the velocity at the apex is 0, and that's what happens a lot of times. There's usually, if you have 2 out of the 3 and there's no other numbers in the problem, there's something that's a 0, and that final velocity is going to be 0. Now, just to clarify this, the apex is not the total time, because the total time would be going up and coming back down. So this is really just the time going up. And I'm going to write that in there just to make sure that I recognize the time up is going for the apex height. So now we have 3 out of the 5. We're good. We're going to solve for delta y. I don't have time in part A, so we're going to solve without time. So coming back here, the equation without time is that third one. So I'm going to grab that picture and capture that. And I'm going to send it here. So that's A. So plugging in the final velocity at the highest point of the apex is 0. So 0 squared is just 0. This is going to be 22.5 squared. And then I'm plugging in plus 2 times negative 9.8. Make sure you put the negative in. If you don't, you're going to get different values than what you should. And then delta y is what we're looking for. So I'm going to do this math and get it all set up. So for the first one, it's going to be 0 equals 500. 22.5 squared is 506.25. And then we have plus 2 times negative 9.8 is 19.6. And that is multiplied by delta y. So this is where some people get into some algebra trouble. They try to combine 506.25 and negative 19.6 and say that delta y is the sum of those two. That is not how it works. This is multiplied together. That is one term. So you can't just like subtract off the 19.6 or combine it with the 506. You got to take it to the other side and do the rest of the algebra. So it's 19.6 delta y is equal to 506.25. And as you can see here, we're going to divide to get this solution. So we're going to divide through by 19.6. So again, just showing you the work, showing you how you should show your steps and such. So that drops out, and we get delta y is a positive value because it's going up, so that makes sense. And I got, for this value, 25.83. It's a displacement, so it's going to be meters. So that is the first one there. Okay, so that's part A. For part B, it asks us for the total time. So we talked about the total time is the time to go up and down. And what I'm going to do is I'm going to solve for the time up. And then let me ask you this. What do you think you're going to have to do to get the total time if we need to put the time up and the time down? If it's returning to the same level, most people just recognize, oh, I'm just going to double that. So if I double that time up, that will get me the total time, which is what I'm looking for. So I'm going to use an equation to solve for time. Again, you can use any of the equations because you have 4 out of the 5 as long as it has time in it. But looking back at these, the easiest one here, I think, is the bottom one. So, or no, I'm sorry, the easiest one, I think, in this case is the top one. So, but you could use the bottom one. It doesn't make a difference, really. So I'm going to take a screenshot of that part and drop it in here and move it over, and we're going to start solving for this one, which is going to get me the time up. So just to kind of recognize that, I'm going to write up here. So the final velocity at the apex is 0. The initial velocity was 22.5. Gravity is negative 9.8. And then we're looking for the time up. So what I like to say here is that I am a positive person. So when I solve this equation, I'm going to take this negative term and make it positive. So I got 9.8 delta t, and this is the time going up, is equal to 22.5. And similar to what we did in the last one here, where you divided by a number and got the variable we're going to divide by 9.8. And solve and get time up. So the time up is like 2.3 seconds. So if the time up is 2.3, then it should come down in 2.3. So we're just going to double that. And the total time is something like 4.6 seconds. So that is our total time up and down value. So that's here. So that was part B. So we got done with part B. Part C says at what velocity is the ball traveling when it's caught. So this you could use conceptual. You could also do this equation again with the total time. Either way, if you did it, you're going to get the same thing. We did this in the last lesson. If you throw something up, when it comes back down at the same velocity. It's just in the opposite direction. So for part C, conceptually, it's going to be 22.5 meters per second. And the thing that you need to include in this, that's the magnitude, that's the size. The direction is the negative sign in front, or you could say that number down. And that makes sense that it moves down. If you leave it as a positive 22.5, somehow the ball has gone up, it's come down, and now it's moving back up again, which doesn't make any sense. So that is the second example problem worked through for you guys. And finally, the third one, this one is just more of the same kind of ideas. A ball is kicked vertically in the air. So there's the ball. It's kicked vertically upward. It reaches the highest point So the highest point is going to be the apex. At 5 seconds, it says, what is the initial velocity, how high it will go. If it asks for how long it was in the air, you would just double this and get 10. So it's on the way up, it's slowing down, gets to the apex, and then it starts to come back down and speed up. Okay, so again, same format, setting up the charts, delta y, bi, vf, g, and t. Filling in the chart. We don't know the initial velocity. We're actually looking for that. 5 seconds is the time that's given. The final velocity, if it's at the apex, and again, I always write this apex above the final velocity. Let me know that's where I'm at. That's going to be 0. And we know gravity. So this one isn't too bad. I think we used the same equation, so yep, it is. So I'm going to use the same equation, Vf equals Vi plus Gt. We got everything except for Vi, so it shouldn't be too bad. 0 equals Vi plus negative 9.8 times 5. So if I solve this, I get Vi is equal to 9.8 times 5 is 49. When you bring it to the other side, it's a positive 49. So 49 meters per second. It's positive, which also makes sense because it's got to go up to start. So that is the initial velocity. So that's part A. Part B is how high did it go? So for part B, you can use any equation that you like as long as it has the variable that you're looking for. And this one, it's that. So I'm going to use this equation, the bottom equation. That's the one that I like for this, if I know the velocities and I know the time, which I do. So we're going to use that equation and plug into it. So delta y is what we're solving for. That's the height, 1/2. Initial velocity is that answer we just got, which is 49. Final velocity at the apex is 0, and the time is 5 seconds. So we're going to do 1/2 times 49 times 5. So this turns out to be 122.5. And that's going to be meters, and it's positive because, again, it's moving upward. So that is the solution to that one. So hopefully you're feeling comfortable with these types of problems and working through them. They're not too bad if you kind of just do the systematic approach that we talked about. So again, step 1, draw a picture. Step 2, filling in your table. Step 3, picking the right equation. Steps 2 and 3, if you can get through those, then the algebra usually isn't too bad for people. But if you are struggling with the algebra, just let me know, and I will try to make sure you are aware of how to approach it. All right, so have a great time and be well.